Okay guys, here we go with all digital design manufacture. I'm going to break this down into sections because otherwise it's quite a lot to take it in one go. So we're going to start off with CAD, and possibly CAM. We'll see how we go. Right, so CAD CAMs. Obviously this stands for computer aided design. Now, there are, as with everything, many pros and cons with this. CAD is a really great tool that designers can use, but they're only as good as the person using them. So, yes, it's really this point here. It can take a very long time to learn how to use CAD. And actually, I'd say there's many levels of learning to use CAD. There's like learning to use CAD to a basic level, but learning to do CAD to this kind of level where you're creating really complex skeletal style structures. That's advanced. Like that takes a lot of skill and training and stuff. So, it's not easy, and it has a steep learning curve. However, there are many pros to CAD. I mean, yes, one of the main things is actually adjustability or editability. Like, CAD can easily change parts of the design, say on this wishbone here, and that can, all these structures here, these can be altered and then they'll update. So if, say, the designer wants to just increase the thickness of that section there, suddenly all of these parts here would update accordingly. Whereas if you were hand modeling or sketching or something, you'd have to redraw the entire thing. And same with scaling. I mean, you can literally scale it up to whatever size you want it to be. And it's great because you can also visualize it. I mean, this could be a rendering, but in fact, I'm going to put that down here as well. You can render or visualize is a really good point with this. Big downsides are, this is a really big problem actually with CAD, is you have no idea what the actual scale is. And like this thing here could be the size of a building. You almost need like, like a little stick man standing next to it or something to give you some indication. Like it could be that big, or it could be completely different in size. We have no idea what the scale is. You can't physically interact with the product either. It's not like you can hold it in your hands. Although this is getting towards the realm of like VR, because they have sort of like tactile feedback now with some VR setups. And that's really what Keanu Reeves is doing with his motorcycle brand. So if you watch that video there, it's really interesting. It talks about how he's using AR and VR to sort of present his designs to clients. And so they can put on VR goggles and they can walk around the bike and stuff. And the next level really is where you've got gloves and you can you start getting tactile feedback. In fact, I'll just add that in there as well. Tactile feedback is a thing that's coming. And also some CAD systems can be very expensive to purchase, and that can be an annual expense. So it can be very, very expensive, and also it depends on the level of functionality that you want from it. So moving on to CAM, like CAM's got all sorts of things that it can do. I mean, if you look at these videos here, you can pretty much make anything with, in fact, you can make anything with CAM now. Like there's very little human interaction with commercial manufacture these days, commercial mass manufacture. Say like this electric guitar body here, like that, all electric guitars now will be just machined out using CNC machine. It's just the advantages are that it's quick, it's quick, not time consuming, is the same. Precision is, I'd actually say precision's the main thing. Precision and accuracy, those are the big things on with CAM. They can make things to a level of quality which is unlike anything you can make by hand. It's funny actually because in this day and age there's a real selling point for handmade stuff, but the irony is that handmade stuff is often not as good in terms of accuracy and precision. So it's very much dependent on the type of product. So generally no mistakes are made. The CAM system will make exactly the information that you give it. So if there's a problem with the CAD file, then there'll be a problem with the CAM file. And there's all sorts of methods as well. Like these are just a few, but like it's worth researching what all these do and like the different types and different operations that they can do. Some CAM processes are 2D, so that's like laser cutting. And a 2D CAM process is where it can't cut. Say if we're looking at a side view here of a piece of material and you want to cut out a three-dimensional shape from it. So we want to cut out, say, almost like a hill shape from that block of stock there. Now, a laser cutter can't do that because this is what we call a three-dimensional shape. So to do that, you'd need to use like a CNC machine, like with the electric guitar body there, because the CNC machine can it can move along. Well, actually, I should draw it properly in 3D, shouldn't I? It's got like 3 axes. It works along like in maths. It's got the X, Y, and then Z, so it can move along all those 3 at the same time. Whereas 2D for laser cutting is different. If you've got same again, if we get the stock material like that, all it can do is just cut all the way through and then just remove a section of material. It can't, unless you're engraving, you can't actually do like profile cuts like that. So that's the only difference really. And CAM, the good thing with CAM, it's getting faster, more, well, not more accurate, it's just getting faster, and it's getting more powerful. I mean, you can cut now pretty much any material on the CAM system. Like these kind of machines here, these are actual tungsten carbide cutter heads here, and the tungsten carbide is one of the hardest materials we have. So with that in mind, it can cut like stainless steel, which is one of the hardest metals that is commercially used. So yeah, and you can literally cut anything with CAM systems now. Okay, so CFD, computational fluid dynamics, this is a way of optimizing the design of things which involve things like gases passing through or liquids. You can see here, this could be simulating an exhaust system or a fan system. Let's call it an exhaust system for a car. This is a turbo system for a car here. So what it can do is it can calculate the airflow or the water flow through something. It can show where either like high velocity areas would be, like around here, or high temperature areas, or high pressure areas in part of a design. And with that, you know how to optimize things like the material thickness that surrounds that. So you know, where do the strong areas need to be, or where do the thick areas need to be, or where do we need to have a heat sink or something like that. And so with this, you can optimize the design thanks to it being able to simulate the actual real world operation of that part there. So that's an incredibly powerful piece of equipment, or incredibly powerful tool we have. That leads on to the next one, which is FEA, so finite element analysis. So whereas this one is looking more at the flow of gas or water around an object, what this one's looking at is kind of the performance of a part under a load or under a certain amount of heat. So you can see here, this is actually a GIF in the slides, but you can see here, this is showing how this I-beam section would perform if a certain load was applied to the middle, and it will highlight where's the maximum stress being applied, and what this will do is it can simulate where the failures might occur. So it could show where the cracks might be, or the areas that would be most likely to fail. So can simulate stress being applied here, and it can simulate things like impacts. So if you had it would even do this. If you had a car driving towards a wall, for example, here, like there's a wall, and you've got a car driving towards the wall, it will simulate what will the car do upon impact. So where will the crumple zones be, and where would the failures be, and where would the most damage occur once the car actually hits the wall. So that's called like event simulation certainly in Fusion's 360. That's event simulation. So, and again, this whole area of FEA is only getting more and more advanced. They're adding more and more capability onto it. So the pros of it are it can be incredibly useful to designers. The old school way of doing this is actually with physical testing. Now, physical testing, if you're building a bridge, and so let's imagine this is a bridge over here. If you're building this as a bridge, you'd have to make a mathematical model. So it'd have to be exactly scaled down using the correct materials. You'd have to add on very specific loads and then see how the bridge performs under that load. Now that's it's time consuming and it's very cost inefficient. And if the model's wrong, you'd then need to remake it again. So it's kind of annoying to do, whereas with CAD, you can do the simulation in a matter of minutes. Then you could change the design. So say on the I-beam section here, if you found that you actually need to thicken up the material, you could change the design or change the material it's made from, then rerun the simulation, see what's the difference in the performance of it. So it's very, very versatile. Okay, we're going to leave it there for FEA analysis.